Greetings, welcome to the 25th lesson in a series of lessons on basics of power systems engineering. In this lesson, I will work through a numerical example of a balanced three-phase system consisting of a generator, a delta-connected impedance load, and the connecting lines. I will calculate for this system the line and phase voltages, real and reactive load power consumption, real and reactive line power losses, power factor efficiency, and voltage regulation. Since there is not enough space on the slides for statement of the problem and the lines of solution that will follow, I will state the questions of this example verbally. We are looking at a balanced system with a delta connected per phase load impedance of 90 plus J75 ohms and per phase line impedance is at 6 plus J25 ohms. Line-to-line voltage of the generator is given as 4800 volts. I have assigned this voltage with zero angle to VAB of the generator as our reference voltage between terminals A and B. To reduce clutter on the diagram, I have marked only one load impedance and the other two will be the same, and have marked the impedance of one of the three lines. The other two are identical. We are asked to find line currents IA, IB, and IC, load phase currents IB, IAB, let me point out here, IAB, IBC, and ICA, percent voltage drop at the load as compared to voltage at the source, real and reactive power delivered to the three-phase load, real and reactive power lost in the three lines, real and reactive power generated by the source, real power efficiency of the lines, and power factor of the combined line and load. The best way to approach a problem of this sort is to convert the delta load to its equivalent Y-connected load, use the equivalent line to neutral circuit to find the line currents, find all of the required quantities for the analysis, and go back to the original delta load and calculate the load phase currents as well as any other quantities that may still be outstanding. I have discussed the general formulas for converting between delta and Y connected impedances in lesson 14, and you can refer to that lesson if you would like to review the general case. However, for balanced loads, the conversion is quite easy. You just need to divide the per phase load of a delta connected set of impedances by 3 to convert to Y. So in converting the load of this example to its equivalent Y-connected load, each leg of the Y-connected load will be assigned an impedance of 30 plus J25, or a third of this value here. As shown on this line here, ZY equals 30 plus J25. The next slide has the Y-connected equivalent load. And here it is. The neutral conductor inserted here is only to help us with our analysis of the system and is inconsequential to the overall function of the system as it does not carry any current. Line to neutral voltage of the generator VAN can be calculated as VAB over square root of 3 with negative 30 degrees phase angle. We're looking to calculate VAN of the generator. And here's the equation for it. Substituting for the voltage, the answer comes to 2771 volts with negative 30 degrees phase angle. Using the A phase line to neutral equivalent of this system, IA will be calculated as this voltage VAN over the sum of the two impedances of the line and of the single phase of the load. And that answer comes to here, IA comes to 44.98 amperes with negative 84.25 degrees of phase angle. I will summarize the essential answers that we have found so far on the next slide. And here they are. VAB was given, VAN was calculated, and IA was calculated following that. Now that we have IA, we can find the load's line to neutral voltage VAN on this side, plus minus VAN. And that's simply the product of the line current times the impedance, the Y impedance of the load. And VAN comes to this number, 1757 volts with negative 44.44 degrees of phase angle. From this, we can find VAB simply by multiplying it by a square root of 3 and adding a 30-degree angle to it, because remember that we're working with the positive sequence systems, unless we're told that the system is negative sequence. And here is that answer, 3000. The line-to-line voltage at load is 3042 with negative 14.44 degrees. We can subtract 120 from this phase angle, and that will give us VBC, that's shown here. And we could subtract another 120 from this to get VCA, or we can add 120 to this one plus 120, and that will also give us VCA, and here it is. VCA is same magnitude of voltage with 105.56 degrees. From IA, that was found over here, we can find IB and IC again by phase rotation. To get to IB from IA, I subtract 120 degrees from this, and the angle becomes negative 204.3. But since the absolute value of the angle is over 180, I'm going to add a 360 to it to bring it between 180 and negative 180. And this is the result for IB. Same amperage, 44.98, with a phase angle of 155.7. And IC is calculated by adding 120 to the phase angle of IA, and this is the result for IC. Since I'm out of room on this slide, I'm going to keep a representative of the answers and summarize them up top here. If we need any other quantity, we can backtrack and retrieve them from previous slides. So here is the summary of some of the answers that we found. Let's now calculate the percentage voltage drop, because we have the VAB, magnitude of VAB at load, and we have the magnitude of VAB at the source. And the percent drop is source voltage minus voltage at load divided by the voltage at source times 100, comes to 36.6. We could have used line to neutral voltages for this calculation as well, but the answer would come out to be the same. This is, of course, a very poor voltage regulation. We can find the load power and line power losses next. For the load power, we multiply VAN this one, by the conjugate of IA, and that will give us the complex power for a single phase of the load. And if we multiply it by 3, that will give us the total complex power for the three-phase load. And here are the values. The VAN at load and the conjugate of the IA. IA is given over here. Its angle is negative 84.25. To convert IA to its conjugate, we simply reverse the sign of its phase angle from negative to positive. Carry out the multiplication, and the three-phase complex power for the load comes to this value in rectangular coordinates. And next we'll find the line power loss. Because we don't have the voltage across the line and we want to save a step, we can find it easily, but we have the current, let's say IA, and therefore we have the magnitude of the current, 44.98. We square that and multiply that by Z of the line, the impedance of the line, and that will give us the complex power for a single line. Multiplying it by 3 will give us the complex power loss on the 3 lines, and that came to this value again in Cartesian or rectangular coordinates. All right, now again summarizing the results for the complex power of the load and complex power of the lines. The real and reactive powers are taken off of these complex powers. We know that the real part always gives us the real or active power, and the imaginary part gives us the reactive power. So they're summarized here. For load, three-phase load, we have 182.1 kilowatts of power and 151.7 kilobars of reactive power. And for the line, we take them from this line, and they are 36.42 kilowatts of active power loss and 151.7 kilobars of reactive power loss. The source power can be found by summing the real parts here, of the load and the line, and the reactive parts of the load and the line powers, and that's done here. For source real power, we have line real power plus load real power, and it comes to 218.52 kilowatts. We add the reactive parts from load and from the line, and that comes to 303.4 kilobars. Of course, we could have alternatively found the complex power of the load as 3 times VAN times IA conjugate for the source. Instead of adding these together, we could have used the equation for complex power. VAN times IA conjugate times 3 would give us the same values that we found here. If I were to substitute the values here, I would have 3 times this value, 200 or 2771 with negative 30 degrees times IA conjugate, which would be the conjugate of this value here, 44.98 with positive 84.25 degrees. I'm not going to carry this out, but if you want to, you can do the multiplication and you should get something very close to 218,520 plus J 303,400 within the rounding error limits, of course. We can then move on to calculate the efficiency as a ratio of the power out of the system divided by the power into the system. In other words, the power that goes into the load that does positive work for us divided by the power that comes out of the source here and times 100 to give us the percentage of the efficiency. We'll use the real power for it, and here it is, 18 or 182.1 was the source power, no, not source, but the load power, real power of the load, and 218.52 was the real power that source put out. The ratio times 100 comes to 83.3%, which is the efficiency of the whole system. Now let's go ahead and find the power factor next. I've calculated two different power factors, one seen by the generator looking into the circuit. And we know power factor is the cosine of the difference in phase angles between voltage and current. So we'll look at the VAN, and it has a phase angle of -30. And we look at the current, which has the phase angle of 84.25. Their difference comes to 54.25. And cosine of it gives us 0.584. Lagging because the current lags the voltage if you compare the phase angles between the two. And another power factor, and that's the power factor of the load itself. And that's calculated similarly. We'll take the difference between the angle of the current and angle of the VAN at the load, and that one is 44.44 degrees. The cosine of the difference comes to 0.768, and lagging again because the angle for current is less than the angle for the voltage. In other words, the current lags the voltage. These are poor power factors. The one seen from here is even smaller than the other one, the load power factor. And that's because the load being a inductive impedance, there's more inductive impedance added to it if you look from here, because the line is also heavily inductive. So that will lower the power factor even further from 0.768 to 0.584. Okay, and in lesson 26, I will use this same set as here, the same setup, well, the one with the delta load, and show how the power factor can be improved with the addition of capacitors at the load or near the load location. I'll now restore the original delta connected load. Here is our original circuit. From IA, we can find the load phase current IAB. Here's IA coming to this node. IAB, the current that goes through this phase of the load in the direction from A to B. The equation gives us IA, if you remember, for positive sequence systems. IA is the square root of 3 times IAB, and it lags IAB by 30 degrees. From here we can find IAB, and by rearranging the terms, and IA becomes to IA over square root of F3 plus 30 degrees. We have all the values we need to put in here. Well, all we needed really was the IA, and the answer comes to 25.97 amperes with negative 54.25 degrees of phase angle. IBC in this direction and ICA are both found from IAB already. Again with phase rotations, so we subtract 120 from this one to get IBC, and we can subtract another 120 from this one, or we can simply add 120 for the phase to the phase angle of the IAB, and either way ICA comes to 25.97 with 65.75 degrees. For added practice, you can calculate the load power using IAB and Z delta, or IAB and VAB, or even V squared over Z delta conjugate, and compare the results with those found here. What I mean by that is we already calculated the load power from the Y-connected impedances, but we can find the load power here if we didn't do it earlier, and that would be, there are different ways of doing that. We have the current through this phase, IAB, we have its magnitude and angle. We just use the magnitude, square it. So 25.97 squared times 90 plus J75 times 3 to get the three-phase power. That should give you the load power. Another way would be to simply do VAB, which we have here, times IAB conjugate. And so let me just put those values in. So we have 3, for that one we have 3042 with negative 14.44 times, so that's VAB, times IAB conjugate of that, which is 25.97 with positive 54.25. And if you find this and multiply it by 3, you should get the same answer as before for the three-phase load. One other way of doing it would be to take the voltage, magnitude of the voltage across AB, which is this value here, square it. So let me just put in the values. 3042 squared over the conjugate of this phase or this impedance. So that would be 90 minus J75. And again, this gives you this single phase power, complex power. You multiply that by 3 to get the three-phase complex power of the load. All these three should give you the same value that we had found earlier for the complex power of the load. We have now reached the end of lesson 25. My name is Fuad Albandi. I'm a PE in electrical power engineering. You find my name and web and email addresses here on this page. The web address is own-your-destiny.mylearnworlds.com, and the email address is own-destiny@yahoo.com. I invite you to visit my website when you have the time. You'll find comprehensive modules on different topics of power systems engineering on that website. Thanks for watching this video. If you enjoy my presentations, please click on the subscribe button and the notification bell. I hope to see you soon in another one of my presentations.